First, we want to thank everyone for coming out to the Senior Design Conference and for our presentation. As Dr. Ledger said, we're the Modular Grasper team. I'm Lindsay Colbert. I'm Janessa. I'm Andre Herrera. I'm James Stillman. Our project this year is sponsored by the SDC Biomedical Engineering Academy Fund, and we're advised by Dr. Stephen Gent and Ms. Ashley Jorgensen Blocker. So the problem that we've been tasked to solve is one that poses a challenge to the robotic industry, and in terms of specifically robotic graspers. A lot of the time the graspers are relatively expensive and they lack versatility in terms of grabbing different things with respect to pressure. So they have issues grabbing a variety of things like screwdrivers or like a chip. And so as well in the industry, a lot of times the graspers are only designed to handle one specific object. So our solution to this problem is to create a gripping mechanism that can apply the correct pressure relative to different objects, including delicate and oddly shaped objects.
So some of our main goals are to use portable and easily accessible parts. So in our design, we use 3D printed parts because that 3D printed filament and 3D printers are pretty easily accessible to anyone and anywhere. And so we'll be using that within our design to effectively pick up those small and delicate objects like chips or other objects such as screwdrivers, other tools. And then we're also to have our device be useful in several different applications. Some of our objectives are to maximize the grasper, so we can that grasper in different mechanisms in different fields, such as the medical field or manufacturing. Maximize the range of objects that are controlled. And then our last objective is to minimize human involvement in the grasper with electronic controls.
So before we began designing our project, we had to first investigate what was out there currently on the market. So we came across these are 3 ones we want to present. So starting on the left, there is a origami inspired grasper. NC State University developed this, and it recently was published in August. And the way this works is it can be attached to a robotic pincher. So the pincher can pull apart 2 strings on the left and right. We close the tendril-like structure in the middle. It kind of creates a cage around whatever it's grabbing. So it can grab things as heavy as 14 pounds or something as precise as a single strand of human hair. And then in the middle, the robot IQ's 3-finger gripper. We took a lot of inspiration from this in our design that you'll see later here in the presentation. It's an open source model, so we were able to look at how they designed their model because they provide their 3D CAD model online as well as their electric code and how they run it. And then on the far right, just a prosthetic hand from Vincent System. This is their 4th generation, and a lot of prosthetic hands like this one are ran with myoelectric sensors, and so they just utilize sensors that detect the electrical activity from your muscles when you contract your hand. And so the prosthetic hand is able to move based on the sensations that are picked up by the sensors.
So these are some of our way to design matrices. For those of you who are just looking at, these are matrices that help us choose between different objects. Each column is a separate choice that we would have, and then the rows define things that we want them to meet. And then they each have a rating 1 to 5, 5 being better. So we ran a test for our mechanism that we wanted to use for our hand. And we had either a gear system, a string tendon-like system, a linkage system, or a pneumatic or hydraulic system. And overall, the string system ended up winning. And the main reasons for it were because our manipulation ease and our fabrication time were more feasible for this project.
Alongside the mechanism, we had to figure out how we were going to manipulate our grasper. And so our 3 categories were manual, cable, and electric. Manual would be just us just manipulating it with our own hand. And then a cable apparatus would be something that spans your upper arm and you can attach to like your shoulder or your elbow, and the grasper would move based on movements of your shoulder or elbow. And then electric would be using motors and Arduino and code to eventually limit the human interaction with the grasper. And so ultimately, the electric did win, but we decided to move that to our second semester goal just because for a time frame that we had, and we wanted to be able to affect the grasping, the grasp of the device before we moved into controlling it with an electric code.
And we had to decide how many fingers or digits that we wanted on each hand. Overall, we ended up wanting, or 5 fingers ended up winning. However, we really want to get that grasping capability down first, so we're going to stick to 3 so we can get the fingers in thumb all the time right, and then add more fingers later on. So this is our final design CAD model. It is a 3-finger, 3-jointing mechanism, kind of shaped like a human hand. It uses a string system with tendons and an elastic band running along the back side of the hand. This back tension, so it opens automatically. And then we plan to put silicone fingertip inserts in. Right now, they're just shaped to put on the end of the fingertips. And then here's kind of a blown up figure of just 1 finger. There's a few channels running along the back and some running inside for the kind of pulling tendon on the front. And the back ones are the elastic band on the back. Currently, they're open to the outside. That's more or less just for our prototyping phase, so we can see inside easier, add tendons, add things that we need, remove things that we need. And the final design will probably end up covering all those up, but they're all nice and thin.
So going into how our string mechanism works, we decided to go with a fishing line to represent the flexors of our hands that run along the inside of your fingers here on your palm. And the way that it works is we have the fishing line strung through the channels that James talked about in the previous slide. And in the fingertip, in that rectangle, there's an anchor. So when you pull down on the string, the finger moves in a sequential movement, kind of like your finger would normally. So it moves from the fingertip to the intermediate knuckle to the base. And as you can see in the bottom figure here, that kind of depicts what it looks like with its curl after pulling off the shoe line.
So on the back side of the hand, we have the extensors, which are going to be the elastic string that we're using. And so these extensors will keep the grasper so that it's at rest, it's open, and then when force is applied to the flexors, it will close, and then as soon as force is removed, it'll spring back open. So these elastic strings sort of work as antagonistic muscle pairs, like what you have typically got.
So kind of bringing it all together, as you can see, our prototype is in the middle there, with the side view, and then our fully 3D printed model is on the right, and kind of just demonstrating, I guess, as you pull out the fishing line, the fishing line flexes it, and then the elastic that Vanessa just talked about fully opens the model again.
To get our prototype kind of figured out, we then need to figure out how much force do we need to pull the tendons with to get a nice strong grip on some of our objects. So we just use a screwdriver as reference and found a coefficient of friction between the fingertips and the screwdriver's rubber part. And we use these 3 equations to figure out how much force we need to pull it with. The top equation is figuring out how much force at the fingertip we need to push with to make it so the screwdriver doesn't fall. We then use the second equation to find the moments at each of the fingers joints. This would give us a maximum tendon pulling force that we need. And if we found the maximum force for that knuckle C, and it was about 1.8 pounds of force we could pull it. We then use the bottom equation with about a 2-inch displacement of how much the tendon is pulled for fully closed. And the 180-degree rotation of our servo motors to figure out that we need about a 0.6-inch radius over an inch across. And using that, and then the 1.8 pounds of force, we need at least a 1.2 inch pound motor get the finger to close fully and provide enough storage to hold over holding. And then we ended up using 25 kilogram per millimeter servo, I believe it is. So we're overshooting it by quite a large margin.
So here's our wire diagram. As we stated earlier, second semester, it's part of our goal to get this electronically controlled. We have our 20 kg servo motor here and our 10 kg potentiometer up on the breadboard. As shown in the video here, once it's all connected, we can rotate that spool that we had calculated in the previous slide. We'll attach that on top of that servo motor and use the potentiometer to turn our servo motor to wind our string to close the hand, and then unwind it and open it back up.
So during the semester, we developed 2 prototypes and we underwent testing to test the grasp of each of our prototypes. Basically what we did was we placed 2 tug motors 12 inches apart and one was filled with geos, one was empty, and then we determined how many we could pick up with each prototype. So our first prototype is on the left, as you can see, and it more or less worked like chopsticks, and so we were only able to pick up maybe 1 or 2 chips at a time. And the reason being was the fingers were too long in respect to the palm. Our first fingers were about 7 inches long, and we decided to then shorten our fingers and add a little bit of a bent palm to get more rounded grasp. So our second prototype fingers were about 3.5 inches, and then the bend in the palm was about 30 degrees. And so we were able to pick up about 4 or 5 geos instead and have more rounded grasp. Again, with the testing, it's just different grab tests. So on the far right, just picking up a screwdriver, fully showing the round grasp with the side view. As you can see, the thumb was able to get fully tucked underneath the screwdriver, whereas before the thumb wasn't even able to get underneath the screwdriver. And then on the left, this is edge can, showing vertically displacing something where the hand isn't supporting it. So you can see that the grasp is tight enough, so the can isn't being displaced due to gravity. So the grasp was tight enough.
So this is our budget for our project. As you can see on this pie chart, a lot of our purchasing for second semester and our future supplies. We have a 3D filament for our 3D printing, and our motors are spec'd at $18. We have about 1 right now that we'll be using to control all 3 vendors, and we'll probably move that up to 2 or 3 in the next semester, depending on if it works to control all 3 with 1 versus 2 motors for the 3 vendors. And then we will add another one to control a wrist movement. And yeah, so our grand total right now is $230. And
so this is a look at what we'll be doing for the rest of this semester, heading into next semester. So after this, we'll refine our presentation for our critical design review with our design committees, and then mostly be wrapped up the first semester after that. Heading into the second semester, we'll continue to refine and test our current design of our grasper, and then do some progress along the way. After that, we'll look at modifying and inserting electric or additional parts, such as that motor, possible pressure sensors, and then potentially a rotating wrist attachment. After that, we'll work on refining that and then comparing that for eventually our senior design. And with that, we invite you to ask any questions that you might have.
Do you think you might have any cable slippage or tangling when you do like just cyclic testing next semester?
we're hoping to avoid that, but we have thought about that and sort of taking it into consideration or just split around here.
Are you guys planning to look into, if you're trying to pick up something really delicate and you like clamp too hard and then it breaks, like looking into that at all?
Yeah, so we're gonna add pressure sensors in second semester. We're looking into adding those to help with sensing how much pressure you're using against the object to avoid question.
Those sensors look like.
They are like, it's like a fingertip, so we, like a silicone fingertip that we can add on to the top of our design. So it will replace. It'll replace this instead of a 3D printed piece. It'll be a
Is
silicone.
that sensor that somebody makes for the finger type application?
Yes, yeah.
How much weight would you like, for it to pick up? Max load?
I think we're shooting for 8 pounds. As of right now, we are at 3 pounds.
Sure.
I guess with that, what's the like restriction, like what breaks before you get higher than 3 pounds?
Just the grasp isn't able, like, we were able to hold it, like, if we were hold the weight and grasp it, we able to hold it, but it's picking it up from the table, the fingers began to unravel. So I think it's just figuring out, the amount of tension we need to have in the fishing lines, that's secure grasp, and pull it up, so they don't unravel.
And the fishing line is pretty skinny as people fish, they know that, so it's hard to pull on it very tight without it hurting your fingers. So your fingers start to hurt before you can actually reach that tension that you need, so. That's also a design that we need to figure out as well.
You have time for one last question? Okay, if we don't have a question, I have a comment. I think my favorite part of the whole presentation was the Cheeto budget at the bottom.
Yeah.
When I saw that, I laughed.
Gotta add it for testing.
Testing supplies, right?
Yeah.
Consumables. Okay, so with that, I guess, good job.